Welcome. Today we are walking through the paper, Attention Residuals. You can see the title, the authors, and their affiliations here. I will guide you through the key ideas, starting from the motivation, through the related work and core technique, and finishing with the experimental results. Here is the key overview figure. It shows the three variants side by side: standard residual connections, full attention residuals, and block attention residuals. This diagram captures the core architectural idea of the paper. Here we can see the core problem addressed by this paper. Standard residual connections, while common in LLMs, use fixed weights to combine layer outputs. This uniform aggregation can lead to uncontrolled growth of hidden states and dilute the contribution of earlier layers, making it harder for the model to learn effectively as depth increases. Notice this key claim. The authors propose attention residuals, or AttnRes, to address the limitations of standard residual connections. Instead of fixed weights, AttnRes uses softmax attention to dynamically select and aggregate earlier layer representations. This allows the model to learn input-dependent weights, giving more flexibility and control over how information flows through the network. This is where the paper explains a practical consideration for large-scale models. To manage the memory and communication overhead of attending to all previous layers, they introduce block AttnRes. This variant partitions layers into blocks, allowing attention over block-level representations. This significantly reduces the memory footprint, making the approach feasible for large models while retaining most of the performance benefits. Here, the paper elaborates on the problem with standard residual connections. While they provide a gradient highway for stable training, they also uniformly sum all prior layer outputs. This means every layer receives the same, unweighted aggregation of information, including the input embedding. This fixed weighting prevents selective emphasis or suppression of individual layer contributions, which can hinder learning in deep networks. This section highlights the core technical contribution. The authors draw a duality between depthwise accumulation and RNN sequential recurrence. AttnRes replaces the fixed sum with a weighted sum, where weights are learned softmax attention scores. This allows for content-aware retrieval of information across layers using a lightweight, single D-dimensional pseudo-query per layer, enabling more dynamic information flow. Here, the paper details how block AttnRes addresses efficiency challenges. While full AttnRes has minimal overhead during standard training, it becomes costly with activation recomputation and parallel processing. Block AttnRes partitions layers into blocks, applying attention only over block-level representations. This reduces memory and communication to O&D, making it a practical, drop-in replacement for standard residuals with marginal training cost and negligible inference latency. This section provides motivation for generalizing residuals. The authors point out that fixed unit coefficients in standard residual updates treat all layer contributions uniformly, lacking adaptability. While highway networks introduce learned gates, they still don't offer a mechanism to adapt mixing across depth. This limitation sets the stage for AttnRes, which aims to provide a more flexible and content-aware way to combine information from different layers. Here we can see the mathematical formulation of full attention residuals. Equation 1 defines the attention weights using a softmax over RMS normed query and key vectors. Equation 2 then shows how these weights are used to compute the final layer output as a weighted sum of previous layer outputs. This dynamic weighting is the core mechanism that allows AttnRes to selectively aggregate information based on content. Look at this pseudocode for block attention residuals. This PyTorch-style implementation illustrates the two-phase computation strategy. It shows how layers are partitioned into blocks and attention is applied both within blocks and across block-level representations. This detailed algorithm demonstrates how the memory and communication overhead is managed, making block AttnRes a practical solution for large-scale models while retaining the benefits of dynamic attention. Look at this result. The scaling law experiments confirm that AttnRes consistently outperforms the baseline across various model sizes. This table shows improved validation loss for both block AttnRes and full AttnRes compared to the baseline. This figure visually reinforces this, demonstrating that AttnRes achieves lower loss across different compute budgets, indicating its robustness and scalability. This table presents a key result: performance comparison of AttnRes against the baseline across various benchmarks. We can see that AttnRes consistently achieves higher scores across a wide range of tasks, including MLU, GSM-8K, and human eval. This demonstrates the broad applicability and effectiveness of attention residuals in improving model performance across diverse domains. This is an important ablation study validating the design choices of AttnRes. This table shows the impact of removing or modifying key components, such as input-dependent query or mixing. The results indicate that each component contributes to the overall performance, with the full AttnRes achieving the best validation loss. This confirms the necessity and effectiveness of the proposed mechanisms. Here, we can see visualizations of the learned depth-wise attention weight distributions. This figure illustrates how AttnRes dynamically allocates attention across source layers. The heat maps show that AttnRes learns to selectively attend to relevant preceding layers, demonstrating its ability to specialize layer contributions and preserve structural information, which is a key advantage over fixed residual connections. In conclusion, the paper successfully introduces attention residuals, replacing fixed residual accumulation with learned, input-dependent depth-wise attention. This innovation is validated through extensive experiments, demonstrating consistent gains across model sizes. The practical block AttnRes variant effectively addresses memory constraints, making this powerful technique feasible for large-scale models with minimal overhead, representing a significant step forward in designing more adaptive and efficient deep learning architectures.